All right, hello friends. Today we're going to be covering the basic equation for physics. Um, if you haven't watched my last video on the kinematics and motion, this is just a basic understanding of pretty much the first unit of what we're going to be covering. But today we're going to be covering the actual numbers and equations versions of the words that were mentioned here. And so we're gonna get into it quantitatively. Most of these equations will be offered to you in the AP Physics formula sheet, as well as with the normal physics, you'll be provided them as well. They might be look different, and yeah, don't worry. I will be making sure that you get familiar with this format as well, other than the ones provided. Just a basic understanding is that x is used as a position, which we can also use as distance and displacement. So that's one of them. So then we have this one over here. That just means this basically, or this. No. If you remember the triangle, it means delta. Delta means difference of. So, for example, delta displacement or delta blah blah blah. It just means final minus O. So if I was, I don't know, 11 meters away from somewhere, and then my starting position was, I don't know, 5 meters, right? My change in displacement, how much did I actually move, would be 11 minus 5. My final minus my initial. Okay. So that's just some basic understanding for these equations. I'll be explaining that later on. But yeah. So let's get into it first. So the basic equations. Okay. So these are known as the kinematic equations, but we can begin with the even simpler ones. The first one could possibly be we would be using the displacement one. All right. So this would be d equals velocity times time. All right. Um, so this basically just stands for this can be either displacement, right? Therefore, this would be velocity, obviously. All right. Remember that special lesson I taught on linear and scalar. Sorry, vector and linear. There we go. So you would linear vectors. So you would remember that vectors have direction, magnitude. Linears only have magnitude. And so that means that if you're ever using a vector, the other components of the equation have to be a vector. This is a very important format for formula sheets and equations in general during physics because, as I mentioned before, it is a very algebra heavy course. And so you have to learn that these quantities are different in terms of linear and vectors. But this equation could also be used for distance. Therefore, this would have to be speed, okay? So yes, there is two variants for this, but you'll get used to it, obviously. But all this just means is that, like, let's come up with a example question for this, all right? Using this equation, all right? So we can say, here, I'll use numbers, all right? There we go. So let's say a car is traveling at around a constant velocity, okay, keep that in mind, velocity of 20 meters per second. All right. And he's doing this for, well, we need time. So for 5 seconds. Okay. So first, we have to ask the actual question for this. So, how far does it travel? All right. So that's what the question is asking. So first, let's read the question, right? A car is traveling around constant velocity of 10 meters per second for 5 seconds. How far does it travel? All right. So let's look at our equation so far. We've obviously learned this one, okay? So d equals v over t. Let's state it, okay? First thing you want to do when you read a question is first, obviously, understand what it's asking. That can be very tricky sometimes. And then also state the components that the question actually provides you with. Okay. So we will be doing two variants for this question, one with numbers and one with variables, just so you can start, or at least I can slightly nudge you into the sense of variable based algebra, since that's how sadly it is done in AP. Okay. So first, let's start with the numbers. We have a velocity of 20 meters per second. Remember, always units, and you can just state it like that. And then 5 seconds. Just an S is fine, but you could also do sec or seconds, up to you. But just for the sake of time, S. Okay. And then it's asking for distance. Okay. This could also be X, but yes. But just for the sake of convenience and understanding, we'll use distance displacement. Okay. So now we have these three components. What equation do we know or have we learned that uses these three? Well, obviously, the only one we actually have learned. And that would be d equals bt. Okay. So let me get a calculator. Go. So let's just plug in the variables we know. 20 and 5. Therefore, the distance traveled would be 20 times 5, which is 100. Remember SI units? Meters. Perfect. There you go. So the displacement would be, right? And obviously, we can't really do this much for variable sense, since this is just a simple equation. So if I just try plugging in with variables, it would just be t equals vt. But you should know that later on, yes, you will be having to deal with variables only, and it can be a bit confusing, but that's fine. Okay, just deep breaths. So let's try rearranging our equation. Okay. In physics, obviously, you'll have to deal with rearranging because they can't just provide you every single formula in the world. Okay, and so let's say here's another question. Okay, this one I'll walk you through. So a runner will completes a what can it be? We can use the track, yeah, 100-meter dash in 4 seconds. Okay, and actually no, it's not realistic. Let's do 10 seconds. Okay. So okay, well, how fast was he running? The runner running. All right. So let's read the question. He completes a 100-meter dash in 10 seconds. How fast was the runner running? Or what was his velocity, basically? That's just another way of interpreting the question. AP or, the people, teachers in general, they'll always try rephrasing what the question is asking for to try and trick you sometimes or like steer you away. But at the end of the day, you just have to know what they're trying to interpret. So yeah, it's very simple. You obviously got this. So let's state the info that the question provides us with. So we have a distance or displacement, doesn't matter, of 100 meters. Okay, there you go. And then time of 10 seconds. Wow, this guy's pretty fast. And then it's asking us for the velocity. Okay. So again, we have the same three variables, but now we're trying to find for velocity. So obviously you got this. We isolate for the variable. So you divide by t, and you'll get v equals d over t. Okay. So a simple trick when it comes to doing these type of rearrangements is that even though when you have numbers, it's much easier to do the rearrangement of the equation before plugging in the variables. Okay, Because let's say I did it without, okay? So you have 100 equals v times 10, okay? So obviously, yes, you could do this. But when it comes to like big types of equations such as Bernoulli's, all right, it's not gonna work out if you plug in everything at the same time. So just a simple tip is to always rearrange before plugging in. And there we go. We have a rearrangement of the equation to find velocity. Now we can plug in, since now we have all the necessary variables to plug in and find the result we're looking for, which is velocity. So here we go. Velocity is an unknown. We have a distance of 2 over 10. Therefore, the velocity would be around 10 meters per second. There we go. Ta-da. Simple as that. Okay. You just have to get familiar with these equations, and overall, it does kind of make sense. I can explain it right now if you want. But let's say you just drew a table, okay? At a velocity of 10 meters per second, that means you're running 10 meters every second. So you have time here and distance here, okay? So this can be very easily interpreted just in real life with like data analysis or any of other sorts. At time zero, obviously, you wouldn't have run. And then 1 second passes, you run 10 meters. And so and so. All right, keeps going. And we can see that there is a interpretation here that this number times 10, right? And then the velocity is 10. So we can interpret that d times t equals the velocity, which makes sense, right? If you traveled 20 meters in 2 seconds, that makes you a velocity of 10 meters per second, because you always want to find the singular sense. So let's say you ran I don't know 150 meters in 3 seconds. You always want to find the singular type of variable. So always go for 1 second or something like that. Okay, and try not to single out that. And once you find that, you'll get the 50 meters per second, and that's your velocity. So it's those kind of things that you can interpret as, and for to understand these equations, definitely do not just try memorizing these. That is not a true understanding of what's going on in physics. And later on you'll understand that a lot of this stuff kind of just makes sense. You see it all around in real life, and you'll get used to it. Don't worry. Okay. So let us move on to acceleration. Okay, this is another type of interpretation. Just before we get into that, I just want to state the actual um, equation that is shown within this thing, equation sheet. Okay. So it may look a bit ugly. Obviously, it's not shown here, but you can always. It's just something super simple. This is kind of what it would look like in a physics sense. So you have the average velocity equals delta x. Remember, x equals distance displacement. Delta equals change of. Okay, so it can be either one of those. Okay, x just stands for position, and then time. Time is always universal. Remember that, and the delta just remembers difference in time. Obviously, if it starts at 0 and you have your final time, um, the delta will just equal this, because anything minus 0 equals the same time. In case you don't understand that, let's say I started at 0 seconds, right? I started running, and then v equals 10 meters per second, distance equals 100, and then time equals. Oh, sorry, that would be wrong. Yeah, let's just say 20 and 2 seconds. There we go. Okay. I did this like this, and then 2 seconds, 20 meters. Okay. So this is my final time right here, t final, and this is my t initial. So 2 minus 0 just equals 2. So that's just an easy trick if you ever like get confused or maybe they're trying to make you waste time. Try to understand that some of these deltas or changes of and sometimes many other things may just equal the number itself. So try to understand why and how these things happen and don't just straight up just do the whole process. You can always skip a few things. In terms of efficiency, don't do it in terms of laziness, but for efficiency. Yeah. So yeah, now we can move on to acceleration. So if you don't remember, acceleration is the actual change in velocity. This can be stated by the equation. So here, I'll just write it down so it's a bit more easy to interpret. Labeled acceleration, symbol A equals delta V or T. That makes sense. It's very similar, and you'll see that a lot of the equations tend to be similar in a sense. This would be delta T. But yeah, so this can be rewritten as V final minus VO. All right, there you go. And remember, if we're starting at 0, delta T just equals the final time. Okay. If VO equals 0, delta V equals T final. All right. So that's just a little statement. So this just means that if we were to change our velocity, let's say I changed my velocity from 10 meters per second and I went to 20 meters per second and I did it in 1 second. All right, I accelerated there. So let's plug it into the equation. A equals, this is my VO, this is my V final, change in T. Oh, this started at 0 seconds. I should state that. At 0 seconds, I was running at 10 meters per second. This can be very important to interpret, especially in some cases, that the time when you start can be like um, in the middle of a run, for example. Like, let's say I was running, and this is when I actually started running, right? Blah, blah, blah. And then here I reach 10 meters per second, then my peak velocity, and then I finish running here. The time of 0, the time where we start this whole process, can be chosen anywhere. And this is something that's very important, and you have to remember this so you don't get tricked. In this case, we're only looking at this area right over here. So in this case, this would be my 0 second for the actual equation, and this would be the 1 second. Okay. So yeah, just try to remember that. Let's move this somewhere else so it doesn't bother us. Here we go. So 20 minus 10, and then since it starts 0, just over 1. So A equals 10. Accelerated at 10 meters per second squared. Okay, remember that? SI units meters per second squared. Right. So that's just a simple understanding. Right. So let's do a few questions because acceleration, if you watched the last video, you know acceleration can be kind of tricky. So we can just make a question to see how exactly it can be like that. Like what type of interpretation can these things actually take? So let's say a bike, all right, just a bike you ride every day. It speeds up from like 2 meters per second to 10 meters per second in 4 seconds. All right. What would be its acceleration? So what is its acceleration? The bike's acceleration. What is the bike's acceleration? All right, there you go. So now we have two formulas, but obviously we know we're trying to find acceleration. So let's just state, actually no, sorry. first we have to read the question and then state the variables we know. Remember that, and then we plug in the equation we know of that corresponds to the known variables. Okay, remember this process is very important. I'm just used to so for this in specific, I know what type of thing I'm doing. But obviously, if you have a question you don't know, you have to do these steps. Okay, so we have a bike that's speeding up, so we know it's changing speeds. It starts at 2 meters per second, so that's its initial velocity, 2 meters per second, and then it changes to 10 meters per second. Okay, so that's it. Velocity final equals 10 meters per second, and this happens in a span of 4 seconds. Oh wow! So what would be the bike's acceleration? Okay, so we have VF, V final, VO, V initial, and then we have universal time, 4 seconds. Okay, and we have to find acceleration. Well, perfect. Here we have just an equation for that. Delta V over delta T. All right. So in this case, because this question doesn't specify, we can assume that it starts at 0. So it would be 4 because T initial would equal 0. Unless otherwise specified or specificated on the question, you can assume plenty of things. This is just for the ease of convenience and time, but don't always do it because they might trick you and they might actually expect you to do that. So yeah. So then let's just rewrite the equation. A equals V final minus VO. Remember, delta equals the change up, so the final minus the initial, and then the time just equals 4. Okay. All right. So now that we have the finalized and most simplified equation, now we can plug in. Remember that process of see, you almost made me do it here. I almost did. I almost plugged in the 4. You always want to find this fully simplified equation with any type of cancel out or just rearrangement, and then at the end you plug in. Okay, so now that we have it, we do the final. So we have all the statements at the top over here. So 10 minus 2 over 4. Okay, simplify even more, and here we go, 2. And then final statement, 2 meters per second squared. There we go. So this makes sense because the difference in velocities is 8, okay? Because look, it went from 2 to 10, the difference being 8. So it changed a total of 8 meters per second. And it did that in a span of 4 seconds. So that just means that that change in velocity divided by that time would mean that every single second it accelerated or increased its speed by 2 seconds. Therefore, it went from 2 meters per second to 4 meters per second in that 1 second. Okay. In this case, acceleration means increasing its speed, but it's not always like that. Okay. Let's do another question regarding that. So let's say a car is slowing down. Okay. So here it's telling you to slow down. But okay, I'm not going to tell you. Okay, let's say just a car goes from 25 meters per second to what? 5 meters per second in 5 seconds, right? Yeah. So what is its acceleration? Maybe as you saw, I removed the actual part of slowing down, and you know, obviously this one still has the speeds up, but it's just sometimes in the question, those are kind of like freebies that let you know what's going on. Because if I know something is speeding up, I know that the acceleration would be positive. That gives me a freebie in terms of correcting my thing. Okay. Because let's say I got a negative 2 meters per second, that means it would be slowing down. So if the question said it's slowing down, then I know it's correct. But if it says it's speeding up and acceleration is negative, then I know something went wrong. So that's why I just switched the second question to say a car is going from, that speed to another speed, and what's its acceleration. that just gives you a little extra step to make sure you know what's going on, and you have to trust your instinct. Basically, you have to know. You don't have to be the best, but you have to have confidence in yourself. Okay, me personally, I never did, but here I am. So it's going from 25 meters to 5 meters in 5 seconds. What is it? Its acceleration. Okay, perfect. So we know that initial velocity equals 25 meters per second. And then it changes to 5 meters per second. So that's its final velocity. And this all happens in a span of 5 seconds. Right? And another reason, and just going back to the question, another reason I made that is just so you try avoiding the terms of deceleration and acceleration. Acceleration doesn't really have anything to do with, obviously, it does have to do with the change in speed, but it doesn't specifically mean that it's slowing down the acceleration. Okay, because let's say the acceleration, you related that to negative speed. Let's say my velocity was negative 20 meters per second. You know, that just means I'm going to the left. Okay, according to the basic axis, and my acceleration was negative 2 meters per second. You can't just relate deceleration to a negative acceleration. That does not mean I'm slowing down. Acceleration is it's just a change in speed. Okay, and in physics, we relate the signs to direction because these are vectors. All right, if you remember, that relates with direction and magnitude, not just magnitude, not just numbers. And these signs help us correspond to that. So this means I would actually be speeding up. If I have these accelerations with that speed, I would be speeding up every second. Okay? So yeah, that's just another statement. So what is this acceleration? You know, here we go. Just implements our thing we've been working on. Practice makes perfect. You know, the more of these problems you do, the better you'll become. So just keep doing that. Any questions, obviously, feel free to leave in the comments. Or just ask your teacher, to be honest. That's what I did. I'm really grateful for that. You know, you have to take that first step, the leap of freedom, or just out of fear, maybe. Um, so acceleration equals 5 minus 25 divided by 5. So acceleration would equal negative 20 divided by 5. So you have negative 20 divided by 5, negative 4. So acceleration equals negative 4 second squared. Okay. So does this mean it's slowing down? Well, in this case, yes, because we know that the velocities are positive and the acceleration is negative, therefore it's slowing down. Since the velocities are positive, that means it's going to the right, according to the standard basis, of course, and the acceleration is negative, which is going that way. So in this case, it's going. Sorry about that. So that means the car is going to slow down because the acceleration is going in the negative direction. And therefore, this change, you know, will result in slowing it down until they're both in equilibrium and end up at 0. Yeah. So yeah, but let's say I was actually going from negative 25 to negative 5. I'll get negative 30 with an acceleration of, you know, let's just say same acceleration. This doesn't mean I'm slowing down since the velocity is in the same direction as the acceleration. So a simple statement would be that if the acceleration is in the same as velocity, they'll go up. So let's say velocity is positive, a is negative, velocity will go down. And then this can be taken obviously as like that, and this can be taken as that. There you go. All right. So if they have the same signs, it'll go up. If they have opposite signs, velocity will go down. Okay. Uh, so now we can move on to just simple Newton laws. So these are kind of like pretty much very important, really. I'll not really be explaining the first one since it doesn't include the equation, but if you are interested, I'll just write it down here. So Newton's law, there's three of them. In case you didn't know, it's fine, don't worry. So the first one, which is it's pretty simple. The first law of motion just states that a body or just anything in general will remain at rest or um, in motion. In motion, this motion would have to be uniform. That just means like non-changing, unless acted upon by a net external force. It would have to be net. Okay, I'll just explain that later on. But yeah, it has to be external as well. So yeah, it just means that anything cannot be like changing. Like if something is if something is just still, it cannot just move with nothing. Something has to act upon it, right? Anything, everything in life, has to have a reference point. Two things acting upon each other, and if it's moving, it can't really just slow down unless something slows it down. Okay, such as friction, for example, right? That's why things or us humans, um, we don't just like keep like for example, I think this is a good example. Let's just take us standing, right? Let's say we're standing on rough concrete and we're just standing straight up, feet flat, and someone from behind you pushes you like straight horizontal, not up, not down, just straight horizontal. You wouldn't move much, right? That's because the friction of the concrete is remaining in place, with your shoes, your feet, anything. Now, let's say I just took both of you into the ice. Okay, you're both standing on ice. It's like North Canada here, ice, all right? And the same person pushed you fully horizontal. You notice that you move, you start sliding. But then over time, you'll start slowing down and slowing down. That's because everything will lose energy. And that friction is still there in the ice, it's just reduced. And so yeah, you can tell that Newton's first law is real. Okay, so let's move on to the second one. F equals ma. Okay, so this just means that the amount of acceleration of a body or anything is proportional to the force acting on it, and then it can also be inversely proportional to the mass of body. This just means that you can rearrange it. So A equals F divided by m, or the m equals the force divided by A. That's just rearrangement, really. And so, yeah, F equals ma. It's one of your best friends. Just remember, if there's a force acting on it, that force will equal a ma. So let's just say we had, I don't know. Um, Actually, no, we'll do the practice questions later. Hmm. Actually, let's do it now. Let's do it now. Yeah. So let's say a 3.0 kilogram, right? We have to be exact. It's similar to chemistry. You also have to use sig figs. And physics, obviously, it's not as strict as chemistry. But just be specific. It accelerates. 3 kg body accelerates. This should be this is a question, by the way. These are just statements. This is a question relating to the yeah. So 3 kg body accelerates 2 meters per second squared. Okay. So what would be the net force, or what would be the overall force? What would be, sorry, would be the net force acting upon the object? Right. So, usually in physics, or at least in AP Physics 1, we will always be ignoring air friction and friction unless otherwise specified. So in this question, we're ignoring, always ignore air friction, but general friction can be, and it should be specified. And if it's not, then it's not there. All right. And then this statement about net force, it just means the overall force, because as I mentioned before, there can be multiple forces slowing down an object or speeding it up. So let's say I had my force of someone pushing me, and then I had the force of friction acting upon me. The net force would be this one right over here minus this one. And so it would look like a smaller thing, but it would still be moving me in that direction. So, yeah. And vectors, addition and subtraction is something we'll cover later on. And here. So let's do this question. So we have, let's read the question. We have a mass of 3 kg. Then we have an acceleration of 2 meters per second. And then it's asking for the F net, or just the force in general. So let's use the equation. F equals ma. We know this. So F equals 3 times 2. The F would equal 6. Oh, and yes, I did not cover this in the last video, but forces, as its creator, or really, or just Newton in general, they have the SI unit of Newton, the big N. Yeah, and you'll see this quite recurring. Yeah, Newton's is the SI unit of forces, and yes. Okay. Let's do another one. Question 6. And I'm just putting a Q next to it so you don't get confused with actual numbers of the laws of motion of Newton. So this is just still in relation to F equals ma. So let's say a force of 10 newtons, all right, the N is capital, is applied to a 2 kg box. Sorry about that. There we go. Question mark. Now we're trying to find the acceleration. So what is the acceleration of the box? Okay. So a force is applied. So we have a force of 10 newton. Then we have a mass of 2 kg. It's a box. Now we're trying to find acceleration. So what equation do we have? F equals ma. Now we plug in, since this is most simplified. Now we isolate. Actually, no. Sorry, I made a mistake there. You would have to preferably isolate for a first and then plug in. So you would have to divide by m. F divided by m. There you go. So now you plug in. It's just something you should get into habit of. There you go. So it has the acceleration of 5 meters per second. Perfect. There we go. Now let's get on to Newton's third law. The third law. This states that basically any type of force applied on an object will have a equal and not negative, but opposite direction reciprocal force. So this can be written as an equation as the force A acting on B equals the negative force of B acting upon A. And we can do, let's just do one question, because this one's quite similar. Let's say a person pushes on the wall mm, with a total force of 50 newtons. Okay. What would be the force acting upon the person? Okay. So this one's kind of vague. It would be kind of confusing if you didn't understand Newton's third law. So this is why you kind of have to understand them. But in case you don't, whenever you actually push against something or anything in general, that object will have a opposite and equal force upon you, reciprocal, right? So let's say I pushed upon this wall with 50 newtons. This wall is going to push back 50 newtons back. And now this is important to remember, but force is a vector, okay? This is because it just is okay. It's a result of vectors, so that's why it's a vector. Therefore, if I'm pushing according to the natural and basic law, if I'm pushing with a force to the right, that will make it positive, and then the normal force, that's what it's called. I'll explain that later. Is pushing back to the left, that would make it negative. Okay, so it would be negative 50 newtons, the reciprocal force. That would be the reciprocal force that's acting upon us, upon the person, really. If you push on the wall, it will act upon with 50 newtons back. That's why you cannot go through it. That's why you can't just push, because it's putting an equal and negative force upon you or on your hand. Yeah. And so this is just a basic summary of Newton's three laws and also the simple equations. It seems we have run out of time. I don't want to make this video way too long so you can easily digest at your own pace and understanding. And so feel free to just try taking these equations into consideration and come up with any type of practice questions or potential questions that you have for understanding, and just practice, and yeah. So I will be covering, so what we did manage to cover was the kinematic equations, and these are just similar equations that you will have to use if you don't have some other variables, okay? Because let's say we have d equals vt. Let's say we didn't have v, we did not have t, okay? Or just any of these. So we never know d, okay? But now we don't know v. This equation is not possible. Any type of equation with two unknown variables is not possible. And so the kinematical equations help us solve these type of problems. Okay, so that's what we'll be covering next video, and also we'll be covering the key relations upon these quantities, or sorry, between these quantities. Okay, and so I'm talking about graphs, and these are a very big factor. Graphs are quite important. AP loves putting graphs on here. Right? So these are the two things that I'll be covering next video, and so you can just practice these normal equations. But just keep in mind, these kinematic equations are obviously more equations, and then these are visuals, but you'll be covering them along with equations. All right. So that would be all for today's lesson. I want to thank you so much for watching, and yeah, have a good day.